morning. Hello, everybody. Hello. A little bit of late start today. Sorry about that. But we're here. We've arrived. All right, so let me kind of pull up here what I need to do. And then we'll have our pre-class talk about what's going on with our lives. And then we will get started with our linked lists. So let's see how many people we got here. Only a few. But the rest can catch up later if they need. All right. So, the first thing I'm going to talk about today is just where we are in the class. I'm reminding you guys that today and tomorrow are our last two lectures. Friday is the final exam, so I'll just kind of talk a little bit about how that's all going to go down and how we're going to wrap up this semester. So today we're going to finish up linked lists completely. Now, we're not going to get to as much linked lists as I want to. I would like to do maybe an example of a doubly linked list, but the truth is we're not really going to have time for that. So you can figure that stuff out on your own. I've given you enough information for that. But for the most part, on the test, there's going to be no doubly linked list stuff. I might ask you one little thing about it, just some like English questions, right? I'm not going to ask you to code anything involving a doubly linked list, but I may ask you just some regular questions, all right? So today we're going to finish up our example using singly linked lists, and that's that. Now tomorrow is a review day. Given our time constraints, there's also one other subject that we have to get to, which is stacks and queues. Similar to doubly linked lists, I'm not going to ask you to code any sort of stack and queue implementation, but tomorrow morning we will talk about stacks and queues. I will give you stacks and queue notes. They're very easy, I assure you. And I will ask you, say, what's the output of this code, but you will not have to code anything stack and queue. You'll just have to know what they are and how to read, say, the output of some program. And it'll be really easy. I'll go over it. Now, the review, I finished it today. If you would like to review the first portion of this class, you can go look at the midterm review. I only did the final exam review as the latter half of what we've talked about. So that's virtuals, operator overloading, templates, linked lists, stacks and queues, and recursion. The final exam will be heavier on the back half of this, all right? I will ask you just a few questions from classes, inheritance, and pointers. But the remaining of the questions will be based on the latter half of this class. So tomorrow we'll go over the review. I will also post answers tonight. All right, I'll upload that video, not the video, but I'll upload the review sheet and all of the answers for the review sheet. So you can get started earlier if you want. I do know that we're kind of cramming a whole bunch of stuff right now. So I don't want you to be too worried about the final. All right, it's going to be similar to the midterm. The last programming question will not be super hard. It will just be something simple. And yeah, so I just kind of want you to go over that review sheet and do your best on the final. And then turn your attention to finishing up the rest of the assignments. All right. I'm here for you if you need me. I told you that I'll do some out of office hours calls with you guys if you'd like. Just let me know. I always like to send messages, of course, but if you really need a call, I'll give you a few minutes sometime. Of course, I do have office hours today, so you can come after class if you'd like. So, if you guys have any questions about that stuff, please let me know. And that's pretty much it. Now, I did briefly explain this assignment yesterday, assignment number 9. I'm just going to go through each function, the skeleton code, and give you a few notes about it. For some reason, I've got 2 Visual Studios open, so we'll do that real quick just so you kind of know what to do. And then we will continue on with our singly linked list. Okay. I think this is skeleton code. Yes, it is. Alrighty. So, like I said, I already briefly explained this assignment, so I'm just going to kind of go through the code real quick with you. All right. So here's your card class. You've done a card class before. For the most part, these will all work. So when I go into the CPP file, I'll show you which functions you may be able to copy paste and which ones you won't. All right. And then here's the deck class. Now this deck class is not the same one as the one you did before. Notice we're using a linked list. We're not doing a vector. All right, we did a vector in the previous assignment. This time we're doing a linked list. So your deck class from the previous assignment will not work here. Now there's a few, these are all the functions I gave to you to code. Some of them I already did for you, but for the most part you'll have to do these ones. Now I said you could add this function if you wanted, so you can do that if you want. I talk about it. And I also said today in the Discord, if you want to add this function too, I will allow you to do that. So yesterday in the SLL that we did here, you notice I have this pushback function here, which we coded. I'll test today to make sure it works. And then you'll notice in the copy constructor, or the assignment operator overload rather, I end up calling pushback like this. So kind of in a way, if you're going to come into this assignment 9 and try to code up the assignment operator overload, you're not going to have pushback, and so you'll have to do it differently. But if you'd like to make it easier on yourself, I will allow you to add this function here, pushback, to your deck class if you'd like, and then you can pretty much just copy this one. All right, so I'm okay with that if you'd like to do that. If you don't want to do that, your assignment operator is going to be a little bit more involved than the one that I did yesterday. This one's only a few lines of code, but without the pushback portion of it, we would have to kind of put this code in the assignment operator, you know, so it's a little bit more confusing. All right, so if you want to do that, feel free. So I'll just kind of make a few notes there. All right, you can add this one and this one if you'd like. So I'm just going to go through the file here. This one is, I think you can copy paste from assignment 2. I think this is an assignment 2 guy. Right, I think I make you initialize these to be null characters, the weight to be -999 or -1 or whatever I told you to do in the assignment. So I think you can get that from there. This one I think will be exactly the same as well. I ask you to initialize the weight value as well. You recall that? So you'll notice it's almost the exact same thing I ask you to do right here. The parameter constructor needs to initialize the weight to be some integer value. I think you could just copy that from assignment 2. I don't think I'd change that up at all. Get card, I think we had this one in assignment 2. What do you guys think? Might as well just pull it up and... let's see. String get card, yeah. So I think that one's the same too. So I think that's an assignment 2. Now these ones are different, all right? These ones are different. I have the weights different here, all right? So this one is different than the one from assignment 2, all right? Right, so there's a less than we did a function for this assignment. Now I'm going to make you do the operator, and this one is different than the one in that. I make you sort them differently. All right, so don't reference assignment 2 for that one. Now this one's super easy, right? As long as you code this one, you can code this one with like one line of code, pretty much. No card will be equal. I mean, there will be no test that I'll do in this assignment where you're going to check for the equality of cards. So I would say you don't have to worry about that. So this could be a one-liner here if you want. And then the get weight, I think that's the same. I got to close that. I forgot to. Let me do that. All right. Do I have that? Get weight. Yep. All right. So for the most part, this is all kind of assignment 2 stuff. These two will be different. Now here's where this changes, right? So in this default constructor, you're going to have to initialize probably these values, the head and the size of the deck, to be null, pointer, and 0. The destructor, you're going to have to maybe call clear list in here, because this has to deallocate the whole linked list. But guess what? As we did in our SLL example yesterday, we talked about clear deck, all right? So you probably just call it there. Now this one, you might want to add pushback for this. Unless you want to do hard mode. All right, if you want to do hard mode there, I don't mind. But like I said, this one will be different. This is the copy constructor. You can probably do easy trick here, as long as you initialize your values. This bracket one here is going to return the node, right? So this one's pretty easy. You've done these a million times already, right? Your dynamic array class, I made you do that. I think in the operator assignment, I also made you do that with the string, right? So this one just returns an element at an index, pretty much, but it returns the actual node. It returns a pointer. All right. What is this one? This is essentially push front. We talked about that one yesterday. Now remove top card. We'll talk about that today. We'll try to do that in class. All right. This one's going to take the top card off the deck. This one's pretty easy. Pretty much you're going to just remove the head in a way. Now this one I'm going to say is different than assignment 2, and I'll talk about that today. I'll talk about why this one is a little bit different. Clear deck, we did that. Sort deck will be, just bubble sort it pretty much with the bracket operator. If I wanted to call the bracket operator on this object, I can do this, just so you know. I could say like this, and then maybe get weight or something. I guess card. Let me see what I called it. I called it a card, all right? So if I want to access a card at I can call the bracket operator here, which returns the node, and then I can access the card within the node. All right, so you can use that. This will return a card somewhere inside the list. So pretty much you can bubble sort this, is what I'm saying. You can say if this J is, say, less than this J plus 1. That's what I'm saying that you're allowed to do. Otherwise, sorting will be a little bit more difficult. It'll be a little bit more involved because it's a linked list, right? That's why I kind of had the bracket operator here, to make sorting this a lot easier for you. But now I come back up to here. Remember, you're going to have to iterate. You have to go through the list. You're going to have to loop through the linked list here. I said we did this one a million times, but now it's different, right? You're going to have to loop through the linked list to find the element at whatever the index is. So it's actually a little bit different. So we talked about sort deck. Now swap cards. This one I'll do in class today. I will do easy mode in class today. If you want extra credit for this, I'll give you some points. I haven't determined how much yet, maybe 10, 20 points. You can make this function better. All right, so today I'm going to do this one in class. I'll do the easy mode. If you want extra credit, I'll tell you how you can make it even better. But you're going to have to do that part. So I'll talk about that. And then the rest I gave to you, all right? So notice I kind of did the getters here. I got a random card index function. This just returns any card or an index for some random card in the deck. And then here, print deck. Notice I call the same thing I was talking about in the sort, right? I refer to this object. I call the bracket on it. I grab its card, and then I print the get card. All right, so I already gave that one to you. So just come back here and watch this video if you need those notes again. All right. You can ask me questions. And that being said, that's kind of all I'm going to do for time spent about talking on this assignment. There is a YouTube video I talked about already. You can just go search for my YouTube channel. It's going to be sometime in May, I think. I think that's about the time. March or May, you'll see the video. All right, when I'm talking about it. So you can go watch that if you need. And that's pretty much it, all right? You can definitely do this, all right? This is kind of a big assignment, but you can definitely do it, all right? It's not going to be super hard, especially since I'm giving you probably the hardest function in here will be this one, all right? And I'm pretty much going to give it to you, unless, of course, you want the extra credit. So we're going to continue on with our SLL. So I'm going to kind of just review what we did yesterday, all right? I'm going to review what we did. I'm also going to attempt to compile this because I want to make sure that it actually is kind of working before I continue on. All right? So we made a templated singly linked list, right? So I've wrapped it in a class. This is pretty much your deck class, all right? This is pretty much the deck class. It's pretty much the deck class. And so you notice up here, I've got this templated node. Now, this is a little bit different from assignment 9 because in assignment 9, you see that the node is inside the class. Now, the reason I did that is because we're working with cards and it's easier. But since this is templated, if I try to put this templated version inside the template class, the compiler gets really angry at me. So we've just made this global, all right? We've just made this global, but that's only because it's a template type. Now, guess what? In assignment 9, if you want to get a new node, I'm trying to think of what in there you'll need. I just want to know if you'll have problems with that before I move on. So just answer me this question while I'm looking for it. So I have the node declared inside of the deck class for assignment 9. All right. So pretend you're in main. Not you're going to have to do this, but in main, how do I declare a node? Take a stab at that while I just double check to see if you'll actually have to do it. Students, I don't think there's any global operators you have to do. Should be fine, should be fine, should be fine. Yeah, I think you'll be okay. But it's a fun question to answer. Let me see. Does anyone know? So it wouldn't be enough to say node. You would have to say deck node. All right. So that might be a little bit confusing to some of you guys. Actually, if I pull this open and look at the bracket, you'll see here I do it. All right. So don't be confused at that because the node is declared within inside of the class. I need to use the scope resolution operator to go and get it. All right. So if you see that, don't be scared. That's just because the node is inside of the deck class. All right. So now I'm done with assignment 9. And now we're going to talk about the singly linked list stuff. So I think I'm connected to Bobby. Yeah. And all I want to do is pull in our SLL so that I can ensure that it is compiling at the moment before I continue on and ruin it even more. All right, we've got some problems. We've got some problems. All right, so that'll be good to fix. All right. So let's see here. So the very first thing that we did was the clear lists, if you recall. So this clear list will deallocate the whole linked list. And this clear list also does the same thing, except this one's recursive. So I showed you how linked lists can kind of be used recursively or iteratively. You kind of have two options here. You can make it recursive, or you can make it use loops instead. So that's just going to deallocate the whole linked list. And then the next thing we did was probably the default constructor and the destructor, right? Our destructor we'll just call linked clear list to clear out the whole list, make sure it's all deallocated. This just initializes things to be default values. And then we probably worked on push front and push back, right? Push front inserts an element at the head of the list, and push back inserts an element at the back of the list. And once we did those two things, we finally did the operator, assignment operator overload. And once we did that one, we then had easy mode doing the copy constructor. Now I'm getting some compiler errors here. Now, what's it saying? It's saying return type specification for constructor invalid. All right? It's saying it's invalid. Now that's kind of odd, but my guess is here, if you notice this SLL here, it doesn't have a template on it. So I think that's what we're going to have to do. For those of you who are finishing up your dynamic assignment today, if you're having problems with this, I think up here in the class, it's fine. I don't think we have to put a T here. I don't think it will hurt necessarily. I think that'll still compile. But in addition to that, we're going to want to come down to our assignment operator overload and our copy constructor and maybe throw a T in there for us. All right. All right, so let's go ahead and see if that's going to compile. Please let me know if that confused anybody, why that was mad, so I can talk about it. And it's still not happy with me. Now, why is that? Why are you unhappy? So this happens to be the copy constructor. That's true. And so I'm actually going to check my notes from my actual notes so I don't get hung up here. We've only got so much time, as I've said before. Okay, so Ali, I thought the reason it was angry was because I didn't template this. So in a way, it kind of assumed that I might do something like this in main. So let's pretend I made an SLL for ints and I made an SLL for characters. And it was assuming that I might try to throw my list in here, in which this calls the copy constructor. But it would be very angry at me because this one is for characters and the my list one is for integers. And so down here, I'm assuming this is why it did it, but I still didn't figure it out. You'll notice that I haven't specified a template type for whatever this SLL is. I haven't specified that. And so if I indicate that whatever this is, it must belong to the same type that the left-hand side is, I think main would enforce that. This still shouldn't work. But for some reason, I'm still getting a... Oh, I know why. I know why. Do you see that? That's why. That's why it's throwing the error. Silly, man. So, Ali, I hope that kind of explained it. I'm not sure if this is necessary, though it doesn't hurt. All right? It doesn't hurt to indicate that this is the same template type as this. As I said before when I was teaching everyone about those templates, I said when in doubt, just template it up, right? When in doubt, just throw it on there. The compiler will be okay with you as long as you throw it on there. But when it comes to the things that the compiler is not okay with, it's kind of hard to draw that line. Does it know that this SLL is the same type as the other one? Will it enforce that? I'm not sure, so I'll just kind of throw that on there to make sure that it knows. So now if I save this, and I remove this in main, I did remove it, it should now compile. That's my hope. When in doubt, throw a template on there. All right, so it worked. If I run my code, it should do something, right? Obviously, I haven't done anything with it. Likely, I could be able to call, say, mylist dot pushback or something. And I could probably throw a 3 in there. But right now, we don't have anything to see how our linked list is working. So let's kind of work on some of this stuff. So let's go ahead and just got to make sure I allocate enough time. Let's work on the bracket operator to start. All right, let's work on the bracket operator to start. That'll be our first thing today. And so this one is in the deck assignment 2, right? This one's in assignment 9. So once again, you're going to have a nice reference for the assignment. So take note of that. This is going to be our bracket operator. All right, and we have to template it up because it's going outside of the class. I also have to indicate that this operator is within the singly linked list class. And so that's what our operator will look like. Everything looks like it's been templated. Notice that the template here, type name T, it's up here. We're indicating that the singly linked list is the same type as the node. The node pointer, at least. So what I always like to do is this. All right. Now notice that this is returning a pointer. And since it's returning a pointer, we can actually return null pointer. I think that'd be fine. So what we'll do is we'll check for our stuff if it's in bounds. So we'll say if our index is greater than, maybe greater or equal to our size, or if our index is less than or equal to 0, or less than 0, rather. And what does that mean? Well, that means it's out of bounds. Now, if we were true C++ coders, we wouldn't print an error message here because we want everyone to figure it out on their own, but we'll say error out of bounds just for fun. And then we'll return a null pointer. All right. Else, we know that it is within the bounds, so we're actually going to have to iterate through this list. So if we're going to go through the list, for those of you who were here yesterday, if we're going to go through this list, what's the very first thing that we should do? If we're about to go through the list, what's the very first thing we should do? Exactly. I always want you to remember that, all right? When in doubt, traversal node. So we're going to need another node, all right? We have to indicate that the node is going to be the same type as the template. It's going to be a pointer. We're going to make ourselves a traversal node, and we're going to say, hey, that starts at the head. That starts at the head node. That starts at our head node. Now we're going to go through this list some amount of times, right? So this one's going to be super easy, in fact. I'm just going to loop through a few times. How many times are we going to loop through, do you think? How many times? Let's pull out our paint here. If I wanted to get the element at the, let me put the indexes in here. You can take a guess at any time you want. But this one is at the 0th index, right? This one's at number 1 index. This one's at number 2 index. So if I wanted to get the element at the 1th index, then I'm going to want to loop through, say, 1 time, right? So attacker says until I is equal to the index. I'd say that's correct. So I'm going to say for I is equal to 0, I is less than our index, I plus plus. What are we going to put in here? Can anyone tell me what's the code that I put in here to move to the next node? We did this quite a few times yesterday, so I do expect some knowledge. What kind of code am I going to put in here if I want to move to the next one? And if you wanna kind of, what's the word, shorten your code a little bit. I know that this variable is kind of long. If you want to call it a T node or something, that's fine. But what code goes in here? I just gotta move to the next node. Do you guys recall? We did it up here. There's something in there. We did it up here, something in there. We didn't do it there. We did it here, kind of, right? We did it here. I'll give you a few more moments. Yes. Well, yeah. For the most part. We're not going to have to dereference that left-hand side because of the arrow. So it's kind of either pick one or the other one. So if you want to use the arrow, then you don't have to dereference it. But if you're not going to use the arrow, you'll have to dereference it. So that moves to the next one. And then guess what? I'm going to return the traversal node here. Should work. And that's it. So are there any questions about that? There's one thing I do want to indicate, and it's that this operator is kind of dangerous because I'm actually returning an address to something inside of the object. So I almost want to make it private, just like I did in assignment 9. It's kind of dangerous because I'm returning an address to something within the object. So if I make it private, I'm not going to allow main to mess with my object, pretty much. So I will make it private. But for the most part, that's going to work, right? Let's pretend that we wanted the element at index 0. Well, we're going to say that node t is equal to the head node, right? Say it's equal to the head node. And then we'll say for I equals 0, I is less than 0. Well, I is not less than 0, so this thing's completely skipped. And then we'll return the head. Now, Reckless, you ask a great question, and you say, are we returning a copy? Yes and no. We're returning a copy of the pointer. We're returning a copy of the pointer, but the pointer still contains the address. Does that make sense? That's a little bit confusing. So notice up here that it's not this. We don't have that ampersand there, right? If we were returning the ampersand, we're returning the reference to the pointer. But in this case, we're returning a copy of the pointer. So yeah, it's kind of like an alias. That's what I'd say. But the thing is that this will kind of go out of bounds. So the alias won't. Yeah. No, you're right. It's an alias. We're returning an alias. But with linked lists, that's okay. All right. And anything else, I'm not okay with it. But with a linked list, it's okay, because we're doing this traversal node thing, right? We have to get through the list somehow. And how are we going to do that? Well, we're going to kind of alias some things so that we can traverse it As long as you're using it correctly, it will not be a problem. But yeah, we're returning a copy of the pointer. So in a way, this is by reference because we're returning the address. So let me see here if things are working. Let me see if things, so I did make this private, but I do want to see if it works. So I'm going to throw it in the public section for now. And then in main, I'm going to want to do a few things. Let's do a getter real quick. Let's do a getter. I'm just going to do this one inside the class. Hope you don't mind. Hope you don't mind. That'll return the size. All right. So maybe I'll do a push front, push back, push front, push back. Push back, 72, push front, 8, something like that. And then we'll say something like maybe 4 into I is equal to 0. I is less than my list dot get the size, I plus plus. And then we'll say maybe C out my list at the bracket. Now this is kind of dangerous, but I want to print out its data, whatever's in there. And let's just see if it worked. If everything works as we intended. You can save, you know. I don't know why it's not saving. Oh. Thank you. All right, so I just inserted 4 elements. I just want to test to make sure that it's all working, that we're having no memory problems, because I don't want to give you bad code. All right, let's take a look here. Let's make sure you can see. All right, so what do? We pushed to the back number 3, and then we pushed, so that's right there, right? You can't see my mouse really, but it's right there. That's the first thing we did. And then in front of number 3, we inserted number 4. So you can see that that got pushed on the head. And then I put 72 in the back, and then I put 8 in the back of that. All right, so singly linked list is working so far. I'm just going to val grind this real quick because I want to make sure that I'm giving you good code, and it looks like I am. All right, looks like I am. Notice we have 4 allocations. 4 allocations. That's because I inserted 4 elements. Isn't that nice? When it comes to dynamic, when it comes to pointer arrays, right? You're gonna this allocation is going to be different. It's going to be, are you inserting, deleting elements? How many times are you deleting and reallocating your arrays? In this case, it's almost a 1-to-1 ratio. It is a 1-to-1 ratio, right? Unless I whip out the copy constructor, but that's beside the point. So that's all working good. So we're going to kind of move on here. I would like to do kind of some important things. I guess I'll leave this public for now, and we'll see if I actually get to this operator down here today. Because the main thing I want to focus on is returning, like deleting something from the list. And then I want to focus on sorting and swapping. So those are our main next things. All right, those are our main next things. So we'll start with this one is going to be, I'm going to say it's a type. So I'm talking kind of about assignment 9 here. And that when I say get top card, I'm going to return a card. I'm going to return a card. But since this is a template type here, I'm going to return a T, whatever it is. So I'm going to return a T, not a type. And I'm going to call remove top element. Maybe remove first element. All right. So that's what we're going to work on now. And this is your get top card or remove top card. Whenever you're playing the game War, you're going to want to remove the top card. So that's what this function is. So our functions are really building up here, as you can see. They're really building up here. Lots of functions going, lots of functions going. All right, so this one's going to be really easy, right? Where is our top element stored? You guys should know that. Where's our top element stored? Reckless asks, for the remove top card, it will return the new head. Oh, so that's a good question. This will return a copy of the data within the old head, deallocate the old head, and adjust the head to the next node. Is that fair? So this will return the data of the old head, not the new top card, but it will return the data within the old top card. So I want you to pretend like you're taking a card off the top of the deck, and you look at it and you say, hey, this is an ace. So we're returning the ace, but we're also taking the ace out of the linked list. Does that make sense? We're going to return the ace, but we're also going to take the ace out of the linked list. It's no longer in there. So this will return a copy of the data within the old head, deallocate the old head, and adjust the head to the next node. Yeah, so we're returning the one we will be removing, pretty much. So maybe I'll speed run this one a little bit, and you'll tell me if I've confused you, right? At this point, we should be comfortable with each other, and you can tell me if I am being too confusing. So, the first thing that we need to do is, well, let's do it in some random order. Maybe you can help me. So let's say I say, I don't know, node T, I'll call it the old head, is equal to head. And then I'm going to say that the head now equals the head next node, right? So this actually updates it. And then what's wrong with this? Can anyone tell me what happens here? What's wrong with this little bit? Can you tell me? So this code will work. Maybe if I put a size minus minus here, it'll especially work. But what's wrong with this? What do you guys think? What is wrong with this code? Is there something that I missed? If you're reading this bit, what did I miss? What did I miss? It's never deallocated, right? That's exactly right. So we're going to have a memory leak here. So maybe I do this. But is this okay? Do you think that's okay? Did I fix it? I fixed the memory leak, but is there now another problem? And what's the other problem? I asked you about this yesterday, too. I kind of did the same thing in some other function. What's wrong with this? You can call it by its memory name if you want. You can call it by its valgrind error. Whatever you say, I'll do my best. Now it's a dangling pointer, right? Well, so, yeah, there's a lot of things going on here. You're all kind of right. So I can fix the dangling pointer by doing this, right? But now we have a seg fault. If I do this, now I have a seg fault. So that's a problem. If I don't do that, I'm then accessing memory that I no longer have. So this is an invalid read or a dangling pointer. And so reckless, in a sense, you're right. We deleted the data. So This is the invalid read, and it is a dangling pointer. So we kind of have to do this. So what do you think about that? Are you okay with that? Notice that this is not a pointer. This is actually a stack allocated variable, so it will be fine. The destructor for this will be called when it goes out of scope. So we'll make a local copy of the data. We'll then deallocate that old head node, and then we'll return the actual item, all right? Well, so since this is not a pointer, Cherry, I'm not going to worry about that. This is not a pointer. This is actually what's called a stack. It's going to be a stack. I got to turn my phone on silent. It's going to be a stack variable. Now, you guys really haven't learned about those yet, so I'm not going to spend time on it. But this thing's destructor will be called when it reaches the end of the scope. So we're okay here, all right? This is what you have to do for the remove top card. Yeah, exactly, Reckless. That's what I'd say. The destructor for this will get called, so it'll be fine. There'll be no memory problems here. We make a deep copy here. We'll deallocate the old head, and then we'll return the item. So let's go test it. Let's test it. Where's my main? I gotta put some big thick lines here so I can find it super easily. All right, so I'm gonna do the same thing, but I'm gonna say cout say my list dot remove first element. And then maybe I'll cout some pretty lines here so I can just see where I'm at. And then I'm going to do the same print here. So this is going to take out, I think, our 4. Let's see how we did. All right, no problems here. Yep. So here you go. That's our linked list right there. That's our linked list right there. And then we removed the top one. That's number 4. And then our linked list head was adjusted to look at the next one. And we're left with only 3 of them. Okay? Are we happy with that? Hopefully we are. So now we're going to move on to the next thing. Now I'll give you one sort. The sort's pretty simple. Given that you have this bracket here, right? As long as you have the bracket, life will be fine. If you're gonna sort without a bracket, you're gonna have like a few traversal nodes pretty much. It'll be a little different. Now, by no means is this the most efficient sort for a linked list, all right? I'm just going to premise this. This is not efficient at all right? For the purpose of our assignment, I spelled efficient wrong, I'm sure. For the purpose of our assignment, whatever this one is works, but this is not efficient at all right? And I'll talk a little bit about why that is while we're doing it. Just keep that in mind, all right? My uncle sometimes claims that he knows computer science. And one day we were talking about sorting lists, the most fast sort out there in the world. And he said, well, that's bubble sort. And then I knew that he didn't know anything about computer science. So that's what I'm telling you guys. If you're ever at a dinner party talking about computer science, don't claim Don't claim that your linked list sorting function is efficient, all right? Don't do it. All right, so I'm going to grab my template here. Now I'm just going to do a bubble sort, all right? I'm just going to do a bubble sort. I is less than, say, get size or size, whichever one you want. I plus plus. Thank you for noting it. I'll find you. Just kidding. I won't. Don't tell. All right, so this is regular bubble sort, right? That's regular bubble sort for I and then for J. Those are our bubble sorts. And then I'm going to check this. I'm going to say if a few things, right? I'm going to say if probably this located at J data is less than J plus 1. It should work, I think. So this calls the bracket operator, right? So that's going to look at our SLL, and it will call the bracket operator. And the bracket operator returns the node. And it returns the pointer to the node. So then we'll go inside of that and use data. Now here's a template question, right? You see this? You see that less than operator? If we use this with our own classes, it's not going to work unless we overload that operator, right? Remember that. That's always a test question I ask. When I'll say, look at this template sort function. Is this guaranteed to work for all types? You'll say, no. Look at that less than. Look at that less than sign. Hopefully it's overloaded. All right, so that's our sort list. And here's what I'm going to do. I'm going to call swap nodes. Now I'm making a function for this. Why is that? Because it's not, well, all right, so there's a few things that we're going to talk about with this. Do you guys know how many ways there is to swap nodes in a linked list? Let's open up our notes. It's note time. We're doing pretty okay on time, so this should be okay. Let me open up my notes here. You guys know how many different ways there is that we can swap elements inside of a linked list? I do ask that question on the assignment, I think. So it's a good thing that we're going over it. So there are 3 ways we can do it. Does anyone have any idea on any of them? I don't think you guys, well, I don't want to doubt anybody. I never want to doubt anybody. So I won't. But do you have 1 or 2 guesses? What's one way we can swap nodes in a linked list? What do you think? If we're looking at this picture, do you guys have any ideas? If I wanted to swap this node and this node, there's a few ways we can do it. Now, it's not as simple as saying temp equals this. Maybe it is, but maybe it's not. So the 3 ways we can do it is, number 1, we can actually dereference the whole node. Now, I don't know if that's okay. Let me think about it. If we're sitting in here looking at these nodes here, I can pretty much say this. I can pretty much just say the head dereferenced is equal to maybe some node dereferenced. Now this one scares me a little bit, but it might work. All right. Now what does this one call? This one calls the copy constructor. This will call the copy constructor for whatever the nodes are, and it will bring in the data. It will also bring in their pointers. So this one's actually bad. So never do this one. This one actually won't work. So you can dereference the nodes. This one's bad. I never want to see you do that one. And that is what you might think you could do in the assignment. You might be able to just say this. Instead of doing this, you would say, well, my node t temp is equal to this one. And then this one is equal to this one. And then this one is equal to this one. This is bad. This is bad. Do not do this one. Your pointers will be all messed up, all right? This is bad. This will not work in a linked list. This will not work in a linked list. So that's bad. Now you could swap the data within the node. Now this is easy mode, all right? This is easy mode. So I could do this. This is easy mode. I could say ttemp here is equal to this data. Now, if you do this on the assignment, I won't give you a 0 for the whole assignment, but I'll give you a 0 for the swap function. All right? I specify this in the assignment. You are not allowed to do this in the assignment. This does not give you enough practice with the linked list part. If I see this in the assignment, I will go in there. I'll look myself, I promise, and I'll give you a 0 for that function. All right, you're not allowed to do this. Does anyone, while I'm talking about the last method, does anyone know any case where doing that might not be preferred? So this is a question that I ask you on assignment 9. I say, let me kind of premise it, I guess. Move the links around. All right, so that's our third option. So this is what you have to do in assignment 9. Do you guys, can anyone think of an example where moving the links around would be infinitely better than swapping the data within the nodes? Do you have any idea where moving the links around is better than swapping the data within the nodes? Take a guess. And if you don't have a guess, that's fine. Before I talk about that, I'm going to write this swap function to move the links all around. That's what it's going to do. So this swap nodes function will be moving the links. That's what we're going to do. We're going to just move the pointers. We're going to move the pointers around. But the nodes will remain the same. So it may seem kind of annoying to swap the pointers around. This is going to be the longest swap function you've ever seen in your life. I'm just warning you. All right? And you might be sitting here going, well, that's lame. Why can't I just do it the easy way? Well, pretend this. All right? Pretend. Assume. What if the data is 1 GB plus? Do you think that your sort function will run quickly? What do you think? If the data inside the node is 1 GB plus and you're just swapping the data within the nodes, do you think your sort function will be fast? Or do you think your computer's fan will kick into overdrive? Yeah, imagine you're moving a train, right? Imagine you have a train that is holding sandbags in the carts. And so would you rather just swap the carts around, or would you rather take all the sandbags out of one cart, take all the sandbags out of the other cart, and then put them in the opposite cart? You know what I mean? Think about it that way. In a train that has carts filled with sandbags, do you just want to move the carts, or do you want to move all of the sandbags out of the carts and then back into the other carts? All right? That's the idea. Write that one down. That's a good example right there. Whoever talked about the trains last time, nice job, right? What if the data is 1 GB plus? Super slow. So in this cards assignment, obviously the data is not 1 GB plus, but you're still going to have to do it this fun way, moving the links, all right? You're still going to have to do it this way. But look here, I'm giving you the easy mode versus the hard mode. So let's talk about swapping nodes real quick. Now, swapping adjacent nodes, can anyone tell me what the word adjacent means? Can anyone tell me what the word adjacent means? Yeah, it means that whatever is adjacent means they're right next to each other. So, excuse me. I'm going to make some copies of some nodes here. So take a look at this, all right? Take a look at this. These nodes are adjacent. These nodes are adjacent, all right? These nodes are adjacent. And so if these nodes are adjacent, how many pointers do we have to update? We have to update this one. I'll make this different color. I have to update this one. I have to update this one. Right, because 3 is now going to point to 4. 4 is now going to point to 5, and 5 is now going to point to this 4. Okay? So that's 3 pointer updates, all right? So that's kind of going to go in our notes here. So for assignment 9, I'm giving you the swap adjacent node function. That's what I'm doing. I'll just kind of give you, well, we'll talk about it later. Well, SLL adjacent nodes are 3 pointer updates. I just showed you that on the whiteboard. 3 pointer updates. Now, if the nodes are not adjacent, I want you to tell me that, all right? How many pointer updates do you think? I'll do some circling. How many pointers are we going to have to update in the, if the nodes are not adjacent? So let me kind of do some circles here. Say we're swapping this one and this one. How many pointers do we have to update? How many pointers do we have to update if we're swapping non-adjacent nodes? Is it 3? It's at least 3. 4, right? Attacker's right. It's 4. I have to update this one. I have to update this one, I have to update this one, I have to update this one. Because even though this one's not getting swapped, this one still has to look at the next one. All right? So are you guys having fun yet? So this is where the extra credit portion comes in, all right? So I'm going to put that in the notes real quick. Here's where the extra credit portion comes in. I will give you the swap adjacent nodes. If you do this, there's 2 things. If you use this function in A9, 2 things you have to take note. In your shuffle function, you can only swap adjacent cards, all right? You can't swap whatever card you want, all right? So let's say you're a little pressed for time on the assignment, which I don't doubt some of you will be. There's nothing wrong with that. And you say, I'm not going to go for the extra credit. You're going to have to make sure that your shuffle function, you only swap adjacent cards. If you try to swap 2 random cards, it's not going to work. Your whole program will break. Same with the sort, all right? Now, I kind of already gave you the sort, right? If you're going to do bubble sort, which I would recommend, you can only swap adjacent cards. And guess what? These cards are adjacent. J and J plus 1 are adjacent. They are adjacent. Now, here's the extra credit portion. Here's the extra credit portion. Make the function swap any two nodes. All right, and so this makes it so sort and shuffle can almost work easier, right? So you might be able to whip out insertion sort here, you know, if you really want to flex. If you really want to flex, if you make the extra credit work, and your function will swap any two nodes, not just adjacent nodes, but any two nodes. Your shuffle function can swap any two nodes, and your sort can do that too. So you might just throw in insertion sort or something just to, you know, prove that it works. You don't have to. You can still use bubble sort, right? Because your function will swap any two nodes, including adjacent nodes. So that's the extra credit. Figure it out if you'd like. Let me do this here. I'll just put it. I'll give you 20 extra points on that. So you can make 220 homework points for this assignment. So I'll give you 20 extra points for that. Now, I'm going to go over the adjacent one, all right? And this is going to be the longest swap function you've ever seen in your life. But we're going to have a good time. So here's the thing, all right? Here's what we're going to talk about, A and B. You guys are following me, right? You guys are not lost in what I'm talking about. I haven't confused any of you. You understand what I mean by if your function swaps more than just the adjacent nodes, right? Please tell me if I need to spend more time on that. Now, I spend a lot of time talking about it in the assignment too. That's kind of a bulk of it. If you scroll down here, you'll see right here, all right? So here's the easy way, and here's the hard way. So I even kind of give you I talk about how to do the hard one, all right? So here's the hard way. This is the extra credit one, and then here's the easy way. This one I'm giving to you right now, all right? So what we have to do in this is identify the leftmost and the rightmost. All right, I'm going to identify the left and the right node. So I'm assuming that, say, j+1, maybe my sort function, will do it like this, where the adjacent nodes will come in at some kind of random order. So I need to figure out which one's on the left and which one's on the right. So we're going to need a few things. For one, we're going to need a traversal node. I'm going to call this one temp because I'm going to use it for multiple things. So this will be our traversal node, and I'm going to start it at the head here. I'm going to start it at the head. This will be kind of our traversal to start. I also need to identify one other thing, the left previous node. Right? So if I kind of pull open my paint here real quick, if I'm swapping adjacent nodes, I need to identify 3 pointers. This one is a walk in the park, all right? This one's easy. This one's also easy, but this one I have to find. I have to find it. I have to figure out what the left previous is. So this is the leftmost here, this is the rightmost, and then this is the left previous. So I have to find those 3 pointers. So starting at the head, here's what I'm going to say. And we have to kind of talk about a whole bunch of cases. So we'll say if the left, so we'll say if A is the head node. How do we check for that? Well, we can do an if statement here. If A equals temp, then we know that A is the head node. And if that's the case, then we're kind of done. Let me kind of do this here. Let me do this. Just for fun, this will help you, I think, with the assignment. All right, so let's assume we've got a left and a right. all right? And so if A is our temp, that means A is the left. Left equals A. That means our right is equal to B. And notice I'm doing some aliases here, all right? I'm using them safely. I promise you, I'm using them safely. So don't get mad at me, please. I'm doing some aliasing, but I'm just trying to make it readable. I promise you I'm using them safely. And then I'm going to say this. Temp equals null pointer. Now this will indicate to me that A is the head. So that's what I'm going to do. By assigning temp to be null pointer, this is going to tell me that A is the head node. But if A is not the head node, I'm going to use this to store my left previous. So you'll kind of see me talk about that as I go down here. All right? You'll see me kind of talk about that. Now I'm going to say else if. We're just going to do a bunch of else if stuff. I'm going to do now, maybe B is the head node. If B equals temp, then I'm going to do the exact same thing. Except I'm going to say left is equal to the B and the right is equal to A. All right. All right. So those are the two easy cases. The two easy cases are, did I check for the head nodes? Now is the hard part. All right. So at this point, if we made it past here, then A and B are not the head. All right. They're not the head. So now we have to do something. So I'm going to do a big else statement here. And I'm going to start traversing. All right, I'm going to start traversing. So I'm going to say a few things. I'm going to do while temp next. There's a few things I need to do. Let's do some just previous checks here to make sure. If A is equal to B, if we're swapping the same node, then I'm just going to return. All right. Because I don't care. I don't care to swap those. And then I want to see if there's anything else we need. And then maybe if the head is null. Now, I'm not saying these cases will happen. I'm just kind of doing some safety checks to avoid seg faults. All right. So now that I've indicated here that I won't have a seg fault, right? That means that head will not be null, so I will be able to dereference it. Go in here and grab whatever the next is. I'm going to say while temp next does not equal null. And this is just going to loop through the list. Are we doing on time? Yeah, we're okay. So while temp next does not equal null pointer, I'm going to check for a few things. I'm going to say if temp next equals A, then I'll say, hey, I know that the left one is A and the right one is B. Why is that? Because I found A first, right? I started at the beginning, so if I find A first, then I know it's the left one. Now guess what here? Which one is the left previous? Does anyone know? At this point, do we know which node is the left previous? Which node is previous to A? Do you know which one it is? Have we stored it? Do we have to go find it? What do you think? Do we know which node is left previous to A? Meaning, is it stored somewhere in any of the pointers? Yeah, exactly. That's exactly right. That's exactly right. So let's kind of whiteboard it just real quick. Let's say this one's A and this one's B. And I said temp is equal to the head, right? Sorry. I said temp is equal to the head. So I look here and I say while temp head next, while temp next does not equal null pointer, if temp next is equal to A, well, it is equal to A, and temp is looking right here. So we found it. We found it. So I'm going to put in a comment here. Temp is the left previous. Temp is left previous. So I'm actually going to break out of here. I'm done. I'm done. I'm done. Now I'm going to do the same thing just in case I find B first. Just in case I find B first. If I find B first, then I'm going to do the exact same thing, except temp will still be the left previous. All right. Temp will still be the left previous. Now, if I don't find A or B, I have to go to the next node, right? I have to go to the next node. How am I going to do that? Well, just like that. This prevents infinite loop, right? Not only does it prevent the infinite loop, it gets us to actually go through the list. So by the time we get to the end of this else here, it's kind of hard to see, but by the time we get to the end of that else, we know what the left, we have the left, the right, and the left previous. We found it all. So we're ready to swap. We're ready to swap. So here we go, folks. Oh, it's time. So I think I will need, well, let's see here. So let's do a few things. For one, let's check to see if temp equals null pointer. Does anyone remember what I said? If temp is equal to null pointer, what does that indicate to us? What does that indicate to us if temp is null pointer? I set it up there a little bit. It was the very first thing that I did. If the temp node happens to be null pointer, I'm indicating something specific about the left and the right nodes. Do you remember? Remember, we have to account for a few different cases, right? Are we swapping adjacent nodes that are deep within the list? Or are we swapping nodes that are right up front? Am I still alive here? All right. So I'll give it to you. I know I'm kind of going fast. This is some scary stuff. But I'm indicating that if temp is null pointer, there is no left previous. There is no left previous, indicating that this is the head node. You remember that? I'm indicating that this happens to be the head node. I'm indicating that this is the head node. So if I set temp equal to null pointer, that means that the left one will be the head node. But if A or B is not the head node, then I'll end up looping through here, and I'll find that temp will not be null pointer. It will be on the left previous node. So if the temp is equal to null pointer, we're going to do some swapping. We have to do 3 pointer updates. 3 pointer updates here. 3 pointers. So how are we going to do it? I might want a... I don't know. Well, actually, no, we don't. So here's what I'm going to say. I'm going to say that the head is now equal to the right node. I'm going to say that the right next is now equal to the left node. And I'm going to say the left next is now equal to the right next node. So those are 3 pointer updates. Let's kind of look at the thing here. So I have to update the head. I have to update the head to do this. I have to say this It's now looking here. I then have to say that this, so that's the very first thing that I did. The second thing I did is the right next is equal to the left. The right next is equal to the left. So that little bit, I kind of did this. I'm kind of doing a lot of moving here. Kind of did that. And then the last thing I said was this. Oh, I kind of messed that up, didn't I? Whoops. I think that'll work. Let's see. All right, yeah. So I have to do it in the wrong order. I have to do it in the right order. I can't update the right next and then set it equal to. Then I'll get an infinite reference. It's going to reference itself. And then you'll get an infinite loop. How do I do that? Don't go to that. Don't go to that link. If I click on this person, I should be able to see their stuff, right? Oh, there we go. Okay. So we'll update the head node. We'll then set the left next is now looking elsewhere. And then we'll work on the right next to look at the new node. All right. Else, it's going to look a little bit different, right? It's going to look a little bit different. So we'll kind of do it in the same order. We'll do it in the same order. And that will say that the temp next is equal to the right node. And then we'll say that the left next is equal to the right next. And then we'll say that the right next is equal to the left. All right. Now that should do it. I know I probably melted your brain a little bit here, but we do have to finish that assignment 9. You know, it's the last assignment. I need to make sure that you can get somewhere on it. So if you're feeling strong, go ahead and do the extra credit portion for this, which will be a little bit more involved, because you'll have to find the left previous and you'll have to find the right previous. You'll have to find the right previous. And you'll have to handle the case that the left node is the right previous. At this point, I'm just ranting. So if you're feeling confident, go ahead and give that a shot. But other than that, we're going to test to make sure that this swap function works. I think I was right. This is the longest swap function you guys have ever seen. Please tell me if that's not the case. And let's see if we can sort our list. See if we can sort our list. Let's see if we can do it. All right, so I'm going to do a few things. See if it worked. Shall we? It's the moment of truth. All right, so where are we at? So this was our initial list, and then I removed the top element, so this is now our new list. And then did I sort it? 78, 72, 23, 28, 3, 1, negative 1, 23. And we had no memory problems. What do you guys think? So we're in the last 4 minutes here. This is the very last thing we'll do about talking with linked lists, all right? This is the last thing that we'll talk about. If we had more time, I would have one more day for linked lists, and we would do a little something with a doubly linked list, but that's okay. If you know singly linked lists, you can definitely do a doubly one. All you have to do is make a previous in here. And then once you do that, you'll just have to add some more stuff to the functions to make sure that the pointers are always looking at each other. All right? You might have to do something like that in CS302. I'm warning you now. So if you've got time this summer, try to implement a doubly linked list if you want. All right? This is the only thing we're going to do for linked lists. So if you've got some questions, please talk to me now. Come to office hours so I can help you. Pretty much everything in here that we've done will help you with the assignment. There's a few things I didn't get to, but I made sure I got to the important stuff. All right, Reckless, you ask a good question. So we do have a few minutes. Let me just see if I can do something like that. But what would be the algorithm say if I want to delete a node in the middle of the list? How do I relink the list? So if you're going to delete, you're going to have to identify a few things. So I'm going to just kind of throw a little bit of pseudocode in here. Let's see, void delete at, I don't know, say in index. I'm not sure. So let's pretend like we had that function. I'm going to speed run this a little bit, so just listen to me as I talk here. Just listen to me as I talk. Hopefully I can help you out with that. So let's say I'm going to delete at that index. So pretty easily, I'm just going to go to that index. But there's a thing here. I need to identify the same three things. The leftmost, well, the leftmost is the index. The right, and then the left previous. I have to identify these same three things. And so I'll kind of just do a little for loop. Int I equals 0. Now, I'm going to make a traversal node for that. I'll call it T node. And I want to start at the head. Now there's a few kind of things in here, right? We're going to have some problems. So it's going to take, how's this? If you would like to really talk about that, I'll give it to you in office hours. It's going to take a little bit of time, but let me do it here on the whiteboard instead. If you're going to delete, say, this 5, if you're going to delete this 5, you're going to have to do two things. You're going to have to identify this node here and this node so that when you take out this node here, let me move this. If you take out this node and you remove it, you're then going to have to take this pointer here, and you're going to have to make sure that this pointer is now linked to that. So pretty much you're going to say left previous next is equal to this node's next. Does that make sense? If you want me to do some coding for that, I'll do it for you in office hours, or you can message me some other time since we are out of time today. But pretty much you're just going to have to identify that left previous node, which is this one. And after you, or like right before you're about to delete this one, you're going to want to make sure that this, whoops, stretches over to here. Does that make sense? Does that kind of at least help? You're going to have to identify that left previous, and then you're going to make sure that you update its pointer to look at whatever this node here was pointing at. All right. So if you guys need me, please come to office hours or send me a message. I said that I would try to do some calls with you guys since we're at the end of the semester here. Tomorrow I'm going to spend the first 20 minutes talking about stacks and queues. We're not going to do very much code. I'm just going to talk about what you need to know, and then we're going to spend the rest of the time reviewing. Today, this VOD will go up on YouTube. The notes, the code, and the whiteboard will go up on YouTube. Not YouTube, but on Web Campus. The review questions will go up today as well. If you want to look at them, we'll go over them tomorrow. And that's that. So thank you all for coming to class today. I know that it was a little brain melting, but I needed to give you enough stuff for you to make that last assignment work, all right? I needed to give you enough stuff to make that last assignment work, and I did. So you guys should be good to go with that last assignment. There should be no problems. For the most part, I've given you a lot of it. You're just going to have to do it yourself. And that's all I got for you. So I hope you guys have a wonderful day. Once again, thank you for coming to class. Talk to me if you need, and I will see you tomorrow. Please come tomorrow if you want a little bit of review. All right? I spill water on myself. You're welcome. You are welcome, sir. Or ma'am. You're welcome. You're welcome. And you're welcome. Thank you. Thank you for coming to class today.